My name is Dan McLoughlin. I'm the Technical Account Manager for Vasco Data Security, and I'm going to take you through a presentation regarding hacking, password hacking specifically, and how it's done, how easy it is to do, and how we can mitigate the risks of this kind of attack in your environment. So, first, what I want to do is take you through the anatomy of what's happening with a hack, and we'll go through that, and then we'll actually see some hacking being done. They are videos that I've done. Just I don't have access to my my main hacking PC at the moment because it's in Belgium. So I did make some videos beforehand for this presentation. So I did do all the hacking on here. So it's a near live hack. What we'll have a look at now is the next steps in this, which is what do hackers do when they're hacking? They basically look to attack the weak spot. So hacking options are varied to your hackers that are out there. There's lots of ways of doing things. There's lots of malware and programmatic things that you can do to hack into systems, and they're all different types of hacking methods. But generally, attackers will go for the weakest point of any system. And in general, that weak spot is the human element. And the human element in the majority of security systems is indeed the password, the static password that's used. So we have to ask ourselves, how can a hacker get my password? So there's two types of attack. There's the basic style of attack and the sophisticated style of attack. So if you're looking at more basic attacks, you're looking at brute force, phishing, and farming. And if you want to go to slightly more sophisticated styles of attack, you're looking at spear phishing, whaling, Trojans, and man in the middle. But what we have to remember is that password hacking is just guesswork. It's guessing, and always remember that it's all about guessing. And what you've got to decide is how you're going to attack the password. Are you going to use an educated guess or just some random guessing? So if we look at the different options for password hacking, you've got the brute force style of attack, which is purely random guesswork. So let's just try every single possible combination of letters and characters and keyboard keys to generate a password. And then you can move into slightly more sophisticated attacks using a dictionary style of attack. So that's where we would take a large list of every possible word that you can think of, or a dictionary file, or previously used passwords in the dictionary file, and run that dictionary against all of the password possibilities. Then we move into rainbow tables. This is where we look at the password hashes that are stored. So a hash is a one-way function to change the password into something else that shouldn't be, you shouldn't be able to reverse engineer. But of course, if you know what the password is and you create a hash and somebody else creates a hash of the same password using the same hashing algorithm, the hashes will be the same. So rainbow tables are just massive lists, gigabytes and gigabytes of lists of passwords and their hashes in the different hashing algorithms. And then we can look at rules. So there are just some basic rules around the password file. So you'd use this alongside a dictionary, say to add 2 numerical digits to the end of every dictionary word that you can find, or capitalize the first letter, or change common letters like S's to 5s and I's to 1, things like that. That's what your rules will do. And then finally, the Markov chains, which basically looks at all the passwords that have been hacked in the past and then uses that information to build up a strategy for hacking future passwords in the file. So I've got a bit of a warning here. There's going to be a lot of numbers coming up in this part of the presentation because we're looking at how long it takes to attack certain passwords. So what we're going to look at here is a slide that I was given many years ago when I started at Vasco in 2007. So it was a presentation that a colleague was giving there, and it was showing how long it would take to brute force a password with 100,000 password guesses per second. And as you can see there, the 5-digit password back in 2007 was still something that was in reasonably regular use, which is why it's highlighted there. But obviously nowadays we're minimum 6, 7, 8-digit passwords and all print characters, at least alphanumeric and lowercase, but also looking at special characters now. So if we look at the bottom right square of that table, the 9-digit password with a 96 possible character all print, so anywhere on the keyboard characters, you were looking at somewhere around the 219,000 years to brute force password. So if we have a look at those brute force benchmarks, the 100,000 passwords per second, that was typical for a Windows password cache file on a Pentium 100 machine, so pretty old technology. If we look at just a modern laptop or desktop with dual processor or dual core, you're looking around 10 million passwords per second nowadays. If you go up to a fairly strong workstation, you're looking around 100 million passwords per second. And if you go to distributed computing or supercomputers, you can start to look around the 1 billion password per second mark. So you can see the incremental steps there you get with technology. So if we have a look at how strong a password is, we take the potential number of passwords that you could guess, the key space effectively, of that 96-digit with 9-character passwords, and you come up with that massive number there. I've put that into my calculator, and it spat it out as it didn't know what the number was. So yeah, I had to do some pretty impressive maths to figure that one out. But it's in the 692 quadrillion mark, so it's a large number of potential passwords there. So if we look at some government-sized cracking power and divide that number by 1 billion, we come out with 21.94 years. Now that's a big reduction on 219,000 years, but still it's reasonably safe. I don't think any of us should be contemplating the same password for nearly 22 years. So we think that a static password might be safe. So I'm going to do, or I'm going to show a video now of a hack that I've done. First, what we need is a password. So most websites will insist on a minimum 6 or 7-digit alphanumeric password. So I've chosen a 7-digit password here, and the password is cracked with a 3 in it. And you can see the hashes that I've generated. So we've got the NTLM hash here, the top hash, the SHA-1, the SHA-256. Now NTLM is actually still used by computers nowadays, even certainly reasonably recent versions of Windows use it, certainly when you're offline and trying to authenticate to a password file stored on the machine. Not so much when it's online onto the network, but still that NTLM hashing algorithm is still in use. And then SHA-256, that's currently recommended by the NIST board in the States as a stable hashing algorithm. The SHA-1 hashing algorithm has been depreciated, so but it's in there just to give you an idea of the length of the hashes, so you can see it should take longer. There's more key data there to be guessed. So let's have a look at hacking this. So what I've got here is a PC that's running something called Hashcat, and there you can see the NTLM hash. And we're going to use this Hashcat software. And first we're going to do a CPU-based attack. So we're going to use the quad-core processor. It's an Intel i7 processor on this machine. We've got the 7-digit password, and we're going to reverse engineer the password. And here you can see it's estimating around 25 minutes to guess that password, to do the brute force on that password. So what I'm going to show now is here we've got the GPU, so using the graphics processor of the machine, and the GPU is much more adept at doing this kind of work. So take the same hash, we put it into the system with the GPU, and we have a look, and you can see that that's already cracked that password. And it was working at 11 billion passwords per second, and it cracked it in 2 seconds. So that's a 7-digit password cracked in 2 seconds at 11 billion passwords per second. So as you can see, the graphics processor, so just on any decent gaming PC, is really good at doing brute force attacks. Oops, sorry, I've knocked the mouse. So let's just get that video back up again. So yes, you can see the GPU is very effective at doing those brute force style of attacks. The 11 billion password guesses per second there. So what we'll do next in this is we'll take the same password, but we'll use the stronger hashing algorithm now, the SHA-256. And here you'll see a slight mistake because I didn't put the 256 algorithm, the hash into the clipboard, so it will fail first time, but then we'll see it on the second attempt. So here we'll take a copy of the SHA-256 version of the hash. So it's the same password, but using a stronger hashing algorithm. So there it is. As you can see, it's a longer string, almost twice the size of NTLM there. And we'll paste that in into the clipboard. And very shortly, there it goes. We'll do a reverse engineer on that password. So same password, remember, same amount of digits, but now it's over an hour to crack that password. So there you go. It's more than double the length of time to crack the password, double the size of the hash, double length of the time. It's fairly simplistic in the way that it works. It's actually more. It can be more than just double length. So here, if we look at the CPU. The GPU doing the same attack, and we can see now that it reckons that it's going to take 1 minute and 44 seconds. And if we just wait a few seconds, it generally cracks the file a bit quicker than that. And the other thing to remember, and this is important with your brute force attacks here, we've got 747 million guesses per second now. The thing that's important to remember when you're doing a brute force attack is that it's not always the last password in the list. So it's not always the worst case scenario that you're looking to protect against it. It can be it could well be the first guess that the machine makes. So you can't take these numbers that you always see quoted are always the worst case scenario numbers. So there you go. You can see that password was cracked in just around 25 seconds there. And yes, and only 23.48% of the key space was used to get to that password. So you can see that you can get, you don't necessarily have to crack the entire key space to get the password out that you're looking for. And that's always important to remember. So the machine that was being used there is a ThinkCenter PC. It's got 16 gig of RAM. As I said, it's an i7 processor. So it's not an outstandingly powerful machine. It's a reasonably strong workstation, and it's got a middle-of-the-range sort of graphics card in there, the GeForce GTX 960. But just to give you an idea of the power of the devices, and the reason that the graphics processors are so adept at doing the brute force attacks is they're designed specifically to do simple tasks very repetitively. So they have many cores on board. So instead of having sort of 2 or 4 cores like your CPU, they have tens and 20s and hundreds of cores sometimes, but just doing very simple processes. So they can run lots of parallel processes at once, and that's why they're very good at brute force password guessing. So we take that strong password, the static password, and the crack time shrinks from the 219,000 years that we came up with to about 2 years for a PC at home and 105 days for a distributed network. Well, that's what I thought, and then I did some research to see what else was going on in the world of brute force attacks, and I found this device out here. This is a 25 GPU cluster, and it cracks every standard Windows password in less than 6 hours. So as you can imagine, that's quite impressive. That's using 8-digit passwords, and that's 350 billion guesses per second. Now I was getting 11 billion, which isn't bad on my cracking PC, but this is racking up 350 billion password guesses per second. So using that device, your 9-digit password could be brute forced in 23 days. That device was actually built in 2012. Now today they've commercialized that product, and it's called the Titan X. And if you buy that with the latest graphics cards on board, an 8 GPU box is running almost the same as that 25 GPU cluster, 311 billion passwords per second. If you scale it up to the 25 GPUs, you'll get nearly 1 trillion guesses per second, and you're looking at around 8 days then to crack a 9-digit all-character password. So that's not good, but we've got to remember here what we're talking about is just brute force attacking. So we're just throwing as much power, computing power, at the problem as possible. We're not actually doing anything intelligent yet. So we have to factor in things like users, keyloggers. So a user's always going to use a reasonably predictable password. Humans are quite predictable in what they're going to use and the way they are going to work with their password. If you've got a keylogger, why bother going to all the expense of building a cracking machine when you can just take the password straight from the user as they're typing it in? If we look at the rainbow tables and the dictionary files, they can really speed up this kind of process. And then there's other things out there, legitimate style software. I say legitimate, but there was a headline of a rent-to-own laptop scheme that had something on it called detective mode. So the store that was renting you out your machine could turn on the webcams. It could log the keystrokes, it could take down screenshots, what you're doing, photograph anyone within view of the webcam, and it would gather all this information and transmit it to the store. So it's not great. So my laptop's a Lenovo laptop, so it's obviously built in China. Well, the majority of things are built in China, but it's a Chinese company. And there were some issues about stuff and firmware on Lenovo devices. So you've just got to remember that there's lots of stuff out there that's going to be potentially harvesting this information. So next, we've looked at what brute force can do, but what happens if we actually do something a bit more intelligent than brute force? So I did some research, and there's a website called Ars Technica, and they challenged one of their journalists who had no prior hacking knowledge to do a hack on a file with 17,000 unsalted MD5 hashes. By the end of the day, he'd hacked 45% of that file. And this was his hacking station. It was a MacBook Air. So not a bad device. But it was an i5 processor, and he actually did almost all of that 45% of that file using about 103 seconds of computing time. He basically spent all day trying to figure out how to use the software. But yes, in the last minute and a half or so of his day, he managed to crack 45% of the file. So it just goes to show how, even with little and no knowledge of this kind of software, you can start to become a pretty effective password cracker. So let's have a look at what we can do. There are data breaches in the news all the time. In the last couple of months, we've seen Adult Friend Finder, the US Tax Authority, IRS, Carphone Warehouse very recently just published that they've lost potentially 2.4 million user records. So there's data breaches out there happening all the time. So if we have a look at a very high-profile breach from a few years back, the LinkedIn attack, so I'm assuming many of you will have heard of and probably use LinkedIn. So I've chosen this attack because it was well publicized at the time. The hashes are easily available to anyone online, and they're stored specifically without their corresponding user ID. So if you want to hack a password file, it's probably the most ethical way of doing so, because there's nothing to tie that password to a user. So we'll have a look at this hack. So again, using the same software, the Hashcat software. This time we're going to use the CPU, and we're using a rule set, a set of rules, the best 64 rules, and we're doing a dictionary attack. So I've got a dictionary file that I found that was particularly good with the LinkedIn set of passwords. So it just shows that there's a lot of work that gets done by other people out there, and you can just go and download the information that you need to crack passwords. Now you'll notice the hash type on this one is SHA-1 hash. So SHA-1 was depreciated by NIST many years ago, actually, and it wasn't ideal that it was being stored in SHA-1, and the hashes weren't salted either, so there was no randomization factor. So what we do is we run this through with a dictionary file, and you can see there you go, we're 0.6 of the way through the file, and already almost instantly we've got 835 passwords. Next time round, 7,014 passwords cracked, now 9,638 passwords cracked in the file in 45 seconds. So there you go, in less than a minute we've got over 10,000 passwords out of nearly 3 million cracked using this software. So it just goes to show how very quickly you can start to brute force these passwords. So next, through the magic of the video, we should skip forward in time to about the end of the cracked file, and there we are. And there you go, you've got 2.2 million out of the 2.9 million passwords have been cracked. And it took just about an hour to do that. So in an hour, nearly 2 million, over 2 million passwords cracked. And if we have a look, sorry, the video gets a bit crackly here, but it will come back up. If we have a look at some of the passwords in that file, we can see the hash on the left-hand side there and the actual the password that was cracked on the right-hand side. So you can get an idea of the password. So let's have a search for a common thing that you might find in a password. So yeah, if you type in LinkedIn, because people were using this for LinkedIn, so they've used LinkedIn in the password, and you can see several passwords there have LinkedIn written in the password name. So this is what I mean by humans being pretty susceptible. Then if we look at CISP, you know, people who are security professionals and should know better, they're actually using their accreditation as part of their password. So it's very important to see that, you know, humans are predictable in the way they work, so we can use that to our advantage when we're trying to hack passwords, etc. So we've seen what I can do. We've seen what a journalist can do who had no prior knowledge. What about the professionals? So the Ars Technica website invited Jeremy Gosney, with his the guy who created the 25 GPU cluster and the Titan X, to attack the 17,000 MD5 file. And he got in that file, he did 90% of that file in 20 hours and did 82% in the first hour. So you can see that was with no, that was purely starting with brute force and then working up his own rules, etc. So no dictionary specific to that file, etc. And that was all carried out on a standard PC with an AMD Radeon GPU. The Radeon GPUs tend to be slightly better at password cracking than the NVIDIA ones, but it's the AMD architectures. But it does sort of sometimes ebb and flow depending on the GPUs that are out there. So some of the sample passwords that were cracked in that session, here you go, you can see Banned Geek 2014, I Hate Hackers, All I Need Is Love, and my personal favorite was the last one here. You won't ever find this using brute force, so you can see that that was attacked quite easily. So how does Vasco help to mitigate the risk on this? Well, the most obvious is through VPNs. Many organizations are using VPNs, and those VPNs tend to authenticate via radius. And often the default settings can be used for the VPN. So what I'm going to show now is how we can attack the passwords used by users with a VPN and radius. So first of all, I've got a little radius client here. We're going to put in a password for a user that we're going to send to a radius server. Just using the standard path and see if we can authenticate. And on that radius server, I've got an audit viewer that we can actually see the request coming in, and I've also got a piece of software in the middle, some hacking software called Cain-Enable. And Cain-Enable is readily available on the internet. Anyone can get hands on it. I did have to run it in a virtual environment because it does crash my my virtual machine when I use it. Sorry, my PC, because McAfee antivirus doesn't like it, so it won't run on my machine. So I had to run it on a virtual machine with no antivirus software. So it does run a little slower than some of the other password attacks that you saw earlier. But importantly, it's freely available out there, and it's quite a strong piece of software because it'll do sniffing straight out of the packets that are being sent to and from the machine. So it's got a network sniffer, a bit like Wireshark on there. So you can see you can take the information straight out of the data being sent to the machine. So in this case, we'll send the password over to the Radius server, and we can see a successful authentication up here. And we'll see on the right-hand side here in the tracking software, we can see the IP address of the Radius server and the authenticator, the encrypted data that Radius creates. So we'll send that to the password cracker. And if we go to the password cracker here, you can see the file, and we'll do a brute force attack. And this is to get the Radius shared secret, which is the key use. Now, to keep the video short, I've used a very short shared secret, but it is alphanumeric, but it's only 5 digits. So if we start the attack on that shared secret, we'll get that up pretty quickly, and you can see it going through and just random guessing all the possible options there, and very shortly will come up, there we go, with the shared secret. And as you can see, it's a word with a 0 on the end, so the O. So quite an insecure shared secret, let's say. I wouldn't recommend using something like that. Now the important thing is, once I've got that shared secret, I can get the password instantly, because the shared secret is used as part of the encryption. So we can just use that shared secret to decode the password. So it doesn't matter how long now the password is or how complex, we can decrypt it almost instantly. So as soon as you put in the shared secret, there you go, you can see the password there. No worries about brute force attack, etc. It's very quick. And now, as a hacker, I can now log in with the password that I've hacked from the user, and I can log into the VPN as that user quite successfully. And you can see logging in now successfully, and those requests going through. So yeah, it's quite important that you realize how easy that process is. Okay, the first part, you've got to get that shared secret, but once that's done, you've got access to every single password. So what we can do at Vasco is we can use one-time passwords, and the importance here is we now have an extra layer of security. So it's a two-factor authentication. So there's a PIN to enter, and you can see it there being entered, and we generate a one-time password. So if we now send a one-time password request over, so we type that in, it's 333232, send that across, you can see it's successfully authenticated. Now, as a hacker, I'd still be able to crack that last password request that's sent through. I can decode that with the shared secret that I found earlier, and we can see the password. But now, if I try and replay that password, it doesn't matter how quick I am to replay it. As long as it's been used, that password cannot be used again. So here we go. If we try and send that password through again, and you can see straight away login is denied. And that's the advantage of using the one-time password. Once that's been used, it can't be used again. And even if someone does manage to see the password that's being used, they cannot reuse it because it is truly a one-time password. And that's really one of the main benefits that we can provide to customers, certainly in the enterprise space, as an additional layer of security to your standard network access and VPN style options. Okay, so we're near the end of this file over. So Vasco provides many different form factors. So you saw there a software token being used. There are hardware form factors available, keyloggers that you might see, keypad devices, that you might see used with your banking style environments. But generally, you'd be looking at the one-button style devices, the credit card devices, and the software devices. So applications and SMS, etc. And Vasco has sold and shipped over 200 million tokens, authentication tokens. So that's more than anyone else in the world. And our philosophy for authentication is to take the three main tenets of user authentication: the security tenet, the ease of use, and the cost, and provide solutions to fit all of those kind of environments, so we can have slightly more secure systems, slightly easier to use systems, or lower cost type systems. So there are products in the range to suit all needs and all different environments, because everyone's environment is different and everyone has their own unique needs. So what about some other methods? Well, the one-time password is great against brute force and keylogging and phishing. But there are sort of man-in-the-middle attacks and social engineering. These are more relevant to application-style security than your standard VPN. But we do have solutions using both Bluetooth or this encrypted challenge response mechanism. The secure channel is the color cryptogram that you see there, to improve the security. So this is the kind of technology that you'll start to see filtering through from the banks and later on into the enterprise space as available. So the server-side solutions from Vasco. So we provide SDKs. Again, that's more on an application level. So if you're looking to secure an application, we have an SDK, and you can see that as like our authentication engine. We provide you the engine, but you can't exactly drive away in it. So there's quite a lot of work to be done. Then there's the out-of-the-box solution. So this is more of an installation. It's like having your own car. So that's our identity server, the federation server, and the appliances. And then finally, there's some service-based solutions. So that's like renting or getting taxis, for example. So some cloud-based authentication as a service solutions. And the identity server, which is probably the most likely to be used in your environment for remote access, it's like a central authentication solution. So it'll work with all your VPNs or firewalls, etc., using Radius. It'll also work with Citrix and OWA and Windows services, things like Office 365, etc. Via ADFS we can plug into. It also has APK, so you can tie it into custom web applications, and also desktop logon as well on Windows machines. So finally, why should you be looking to use Vasco? Well, we offer banking level of security. It's tried and tested technology. It scales from 5 users to millions of users. It's very quick and simple to use. It's quick and simple to set up. And we have flexible solutions to fit all budgets and security requirements. So that's pretty much the end of the presentation. If you've got any questions, I'll start unblocking the line so you can unmuting line so you can ask. But yes, please feel free to ask any questions.
Parrot here.
And we can go from there.
What's the wrong number?
I think it's this is just sales.
Got the wrong number. The term is Parrot. No what they're expecting from second order.
Yeah.
Okay, so if there are any questions, please feel free to ask. I might.
IE11 has caused some significant problems across the world with it doesn't work the same as 9 in terms of it.
Right, I'm sorry, I'll mute that one line because I don't think they're asking us specific questions there. So yeah, if there are any other specific questions that anyone has or would like to ask, please feel free. Otherwise, you can contact Wickhill and ask them any questions, and they can be passed along. But certainly do get in contact if you found this useful and give us some feedback. That'd be very good.